Hello everyone. Welcome to the second lecture. And in this lecture, we'll start to talk about the electric force. Everything we talked about in the previous lecture was like kind of an introduction and learn about some of the property of the electric material, about the charge. Now, in this lecture, we try to describe the interaction and try to put that in a formula. Similar to what we did in the gravitational force. You remember like when we did what we did in physics 1, when we described the gravitational force, we said like if we have mass 1, point mass, and point mass 2. Even like if this mass has a size, we always consider the center of mass as the location of that object. And we say like because of the mass, there is an interaction between these two objects. And what kind of interaction? As we described in physics 1, it's attractive force. So M1 and M2, they attract each other. And we said like the force that the first mass exert on the second mass, and we can call this one F1, 2. And there's also a force that M2 exerts on M1 and this. So if this is like, we can say like this is F1, 2, this will be F2, 1. So that's the force that the first mass exerts on the second. And this is how I use this one. And here we have F2, 1. And we learn from Newton's third law that these two forces, they are equal in magnitude and opposite in direction according to the Newton's third law, action and reaction. And we say like F1, 2 equal F2, 1. That's what we did in the previous course. Now the question is, how much or what are the factors that control this force? If I want to see like how can we describe this force, what are the parameters or variables that affect this force? We said like this force is proportional to M1 and M2. So if we have heavier masses, the force between these two will be what? Will be proportional. And also we say like it's inversely proportional to what? To the distance. So if I define the distance between these two masses by distance or by length r here, which describe the distance between the center of mass of these two objects, we will see that this force, which it could be like F1, 2 or F2, 1, by the way, it's proportional to the masses and very proportional to the distance. And then we said, based on that, I can translate this statement into an equation. And in this case, we say like F equal constant times M1, M2 divided by R squared. And by the way, this is like what we call like the magnitude. And then if you remember, we describe this constant by the gravitational constant, and we use the capital letter G as a way to describe it. That's what we did here with this one. Keep in mind that the action and reaction say like the two forces are equal in magnitude. So F1, 2 equal F2, 1 as a magnitude, they are equal. But as a direction, they have opposite sides. So, and how do we know the direction? If we put like this arrow, it means like we are dealing with direction. If we put like the absolute value here, we are looking for the magnitude. Or if we drop the the vector arrow, then we can write it this way. So this is another way. So as a magnitude, they are equal. As direction, they are opposite. That's what we did in the gravitational force. Now the question is, okay, can we do the similar thing but for the electric force? Actually, yes. And we will see like if I have a point charge, and we'll try to ignore the size at this moment here in this case, and I will call this one Q1, and there is another point charge, and this will be what? Q2. Sorry. Now Q1 could be positive or negative. And this Q2 could be positive or negative. Now, let's not worry about the sign at this moment. Let's try to talk about the magnitude. We'll talk about the direction in a moment here. And then I say like, we define the distance between these two as r. And also we will assume that the space between them is what? Is vacuum. Okay, so in this case, we know that if we are trying to do the same thing with this force, how can we describe it, and what are the factors that control this force? So how can we describe this force? Now we know that when we have like two charges, they will interact with each other, and this interaction could be attractive and could be repulsive. And we know like if we have two positive, we will have what? A repulsive force. If we have two negative, again we'll have what? A repulsive force. If we have positive and negative, then we'll have an attractive force. Now let's not worry about the direction at this moment, just let's worry about, as I said, about the magnitude. So in this case, as I said, we assume that we have 2 point charges with a distance r, and the space between them is vacuum, as I said. Now the question is, what are the parameters that control this interaction? We will see like the force between these two, and by the way, the force that the first charge exerts on the second charge, if I call this one F21, and the force that the second charge exerts on the first charge, F21, here, these two forces, F12 equal F21. But this is the force that Q1 feel because of Q2. And this is F12 is the force that Q2 feel because of the charge 1. And as a magnitude, they are equal. As a direction, they are opposite. Now, these two forces, F12 or F21, is proportional to Q1 and Q2, and that makes somehow sense. More charge, stronger force, more interaction. So we know that this force that we are describing here at this moment here, let's choose F12, is proportional to Q1 and Q2, and that's not the only parameter. And also we have another parameter that also controls this one, which is the distance. If they are close or far away, this also will affect the magnitude of this force. So the force actually is affected by the distance between these two masses, and also with the magnitude of the charge of each one of them, or like both of them at the same time. And how is the distance is affecting this one? Similar to what we did in the gravitational force, it's inversely proportional to r square, or it's proportional to 1 over r square. And this is like the two parameters that control this one. And again, we assume that this one is in the vacuum, means like there is nothing in between. Now if we place that in a different material, for example, let's say in the water or in a different type of material, then the interaction will be a little bit different, and we'll talk about that later on when we talk about the dielectric material, and we'll deal with that when we talk about the capacitor. But for the time being here, we will assume that always the space between these point charges is always vacuum. And in this case, I can translate this statement, which is the proportionality, to an equation, and then we say like F12 equal constant, because when I say like F1 is proportional to this, it means like these two quantities are linear, which means like F is linear with this whole thing, Q1, Q2 over r square. And linear means what? Constant times Q1, Q2 divided by r square. And this constant here, I will call it K. And we'll see like how much this K in a moment here. So F12 equal as the magnitude or the force between these two charges equal K Q1 Q2 divided by R square. Now, again, what's Q1? It's the magnitude of the first charge. What's Q2? It's the magnitude of the second charge. And R square, it's the distance between these 2 point charges. Now, K here is the constant. And this K, by the way, depends on the units that we are using. And if you look at this constant here, and we call it like the column constant, it's equal 8.99 times 10 to the power 9. This is a number. You don't have to memorize it anyway. It will be always in your cheat sheet, and you can always find it if you need it. It's 8.99 times 10 to the power 9 in Newton meter square per column square. So whenever we are using this quantity here, this number, keep in mind that the length unit we will use is the meter, the charge should be column, and by the way, Newton here means like kilogram, if you remember, meter per second square as a way to describe it, so we should be familiar with that. So this is like the quantity of this constant in the SI unit. Now we will see later on that this K can be described by another type of constant, which we call the permittivity of the vacuum. So since we assume that the space between these 2 point charges is a vacuum, so there is something we call like the permittivity of the vacuum, like which is somehow will tell us like how the medium will affect the interaction. In this case, we will just use it for the vacuum, as there is no material, there is nothing that will affect or screen this interaction. So that's why we will use the letter here, epsilon naught, as a way to describe this column constant. So K actually equal 1 over 4 pi epsilon naught. Keep in mind that epsilon naught here is defined as 8.85 times 10 to the power minus 12 column square Newton per meter square. This is, again, you don't have to memorize this one. So according to that, we can now write the force or describe the force, the magnitude of the force actually, in terms of the electric permittivity of the vacuum as 1 over 4 pi epsilon naught. But the whole thing here, as we said, that's equal K, and that's equal 8.99 times 10 to the power 9. In many cases, by the way, we can describe K, roughly speaking, as 9 times 10 to the power 9, as you think about this one, as instead of the 8.99 times 10 to the power 9, we can describe it as 9 times 10 to the power 9 Newton meter square per column square. That's, in some cases, we can do that. Anyway, now the question is, okay, what about the direction? Our next part will try to describe the direction of this force, and the direction is very important, because if we have different or many particle or many or system of point charges, we need to identify the direction of each force or each pair in order to find the net force exerted on one of these point charges. We'll talk about that in our next video.